let's look at another example of a pipe flow, and our approach here is going to be a graphical. So basically, we can compare the Inviscid versus viscous, and it's going to give a little intuition to the problem. So the problem is we have a pipe system. Let's assume it's like this, right? So it starts from here, it goes up, straight, again goes up, straight, and then there's a valve here. And then it goes down and out. All right. And basically the question is to calculate the head needed to achieve a certain or a specific volume flow rate. So let's name the locations along the pipe. So let's call this A, B, C, D, E, and F, G, H, and I. Okay, now what I'm gonna do here, I'll try to use a graphical way. Let's see if I can get this to work. All right, that should be good. Let's see, let's do this. And then these two CV here. In a moment, you're going to find out what I plan to do. A, B, C, D, E, F, G, H, I. So I need one more. Yes. CV. And move this here. All right, that looks good. Okay, so and let's name the station. So it's A, B, C, D, E, F, G, H, and I. Okay, so we assume that the pressure at the inlet PA is here, PA. And let's first consider the case of Inviscid. And I'm going to use the blue, light blue, for Inviscid. So what happens? Inviscid, as we go from A to B, so the y-axis here is the pressure, and the x-axis is along the pipe. It's not really the horizontal distance, it's just along the pipe. So it's like a S, if you remember, for the curvilinear coordinate. So going from point A to point B, if it's Inviscid, it's a straight pipe, so there's not going to be any pressure drop. Going from B to C, there's going to be a pressure drop, right? Because you go from a lower height to a higher height, so you need to push the water. Pressure at the bottom is rho GH, and as you go up, you lose pressure. So there's going to be a pressure drop from B to C. Now from C to D, again, no pressure drop. D to E, same pressure drop, assuming that the length is the same. Now D to E, right? And then E to F, it's a horizontal pipe. F is a valve, but if there's no viscosity, valve is not going to do anything. So it's just going to continue like a straight line to the point G. And then G to H, we're going down. So the pressure is going to basically increase, right? And then H to I, no pressure difference. So if someone asks, what's the head needed? What's the pressure difference needed? You say, well, this is a pressure at upstream, this is a pressure downstream, and this is the delta P needed, right? Now, what happens if we take viscosity into account? It becomes really interesting. So if we take viscosity into account, and I'm going to show that by, say, this color, from A to B, there is a pressure drop, right? It's not going to be straight. There's going to be a pressure drop because of viscosity. From B to C, well, we have pressure drop because of moving against the gravity. So potentially the same slope, but then because also we have friction, so the slope is going to be sharper. So the pressure is going to drop further than the pressure drop in the case of an Inviscid flow. Again, from C to D, from here to here, here to here, along a straight line, but the pressure is going to drop a little bit. Okay, as you can see, already we need this much extra pressure. Now going from D to E, well, it's going uphill. something parallel to that, but a little bit more, right? And then we know how to calculate exactly what the value is, but this is just a graphical representation of what happens. Now, from E to F, again, a straight line, so it's not going to be flat. Pressure is going to drop. Now, something really interesting happens at F. So at F, there is a sudden pressure jump if viscosity exists because of the turbulence that the presence of valve induces, right? Now, the valve doesn't need to be closed. Just the fact that there is a valve, there's non-uniformity in the boundary of the pipe, that's going to cause some turbulence and pressure drop. So pressure is going to drop instantly over the valve, right? And again, we know how to calculate that. Now, going from F to G, without viscosity, it's going to be straight. With viscosity, it's going to be a little drop. From G to H, well, we have to regain some of those losses. If it was inviscid, it was something parallel to this line. But now, because it's viscous, it's not going to be as efficient as that one. So we're going to just recover a little bit of the pressure, right? Here. Then going from H to I, it's supposed to be a straight line, but then it's going to be a little bit down. So in the presence of viscosity and including minor and major losses, this is really the delta P needed to get the flow going with the same volume flow rate inside the pipe. Okay, and again, we can very easily calculate once we know the length of the pipe and the diameter of the pipe, the length of each segment and the diameter of the pipe, the density and viscosity. We have all the tools to exactly calculate the slope of each of these curves and exactly calculate, well, as much as we can based on the available experimental data, what pressure head is needed to move the flow inside the pipe. But again, as you see, this gives us a little bit of physical intuition of what happens and where, I mean, if you do it very accurately, where we're going to have the maximum losses. Maybe we can move the valve or do something about it such that it becomes more efficient. And particularly, this is interesting to pay attention to, that at the valve or a bend or a T, we definitely have a sudden pressure jump.